Automotive Safety Systems Explained. Passive Safety Systems. While many features are built into vehicles to help avoid accidents, they cannot be prevented entirely. Because of this, much emphasis has been placed on the protection of occupants in the event of a crash.
Safety features that help protect the occupants in an accident are generally passive because they do not require driver input to activate the system. In this program, we'll discuss passive safety systems.
Because motorists don't always take advantage of active safety systems, like buckling a seatbelt, automatic or passive restraint systems, which don't require action on the part of the occupants, were developed. Passive systems include automatic seatbelts, inflatable restraint systems or airbags, head restraints, padded interiors, and even the design of the vehicle's body structure and components themselves. The automatic seatbelt automatically fastens the seatbelt around the occupant when the car door is closed. These belts may run up and down the door frame or attach to the door pillar and swing outward as the door is opened. For complete protection, however, the occupant must remember to fasten the lap belt. Other vehicles have had the seat belts attached to the door itself. As the door is opened, the lap and shoulder belts swing outward with it, allowing passenger access.
Passive safety design features aim to improve the crash worthiness of vehicles. Good passive safety systems are designed to ensure that only tolerable loads are applied to the occupant's body during a crash. This is done first by restraining the occupant within the passenger compartment with a seatbelt or other device in order to reduce the chance of making contact with the interior parts of the car. When contact cannot be avoided, the structures, which are likely to be hit by the occupants, must be designed to collapse and cushion the blow. Science tells us that the impact that takes the longest from beginning to end will be the softest. Look at what happens when a ball is thrown into a catcher's mitt. The ball, thrown at high speeds, hits the mitt and compresses the padding. The padding deforms and allows the ball to decelerate slowly, which in effect lengthens the impact. At the same time, the catcher moves the mitt and ball inward, further lengthening the time the ball has to decelerate. Of course, all this happens in the blink of an eye.
Automotive designers use the same principle of lengthening the impact to design crash worthiness into their cars and trucks. Passenger compartments are reinforced with steel. Hoods and body panels are designed to crumple. Engines and transmissions are designed to deflect downward. To better understand this, let's look more closely at what happens in a vehicle crash.
In a moving vehicle, it must be remembered that the occupants are traveling at the same speed as the vehicle. The moving vehicle and its occupants represent kinetic or moving energy. In a crash, things happen very quickly. The total time from the point a vehicle contacts an object and begins to decelerate until the vehicle stops moving and the damage to it is completed occurs in approximately 200 milliseconds, or 0.2 of 1 second. In about half that time, or 1/10 of a second, the occupants will come to a halt. This means that in a frontal collision, after the front of the vehicle decelerates, the occupants will continue to move forward. Very quickly, the rest of the vehicle structure also decelerates, and within 40 milliseconds, the occupants are beginning to leave their seats. Since they have only the space between them and the inside of the vehicle to travel for deceleration, they too will soon stop when they contact the car's interior. If this deceleration is too rapid, the forces on the occupants' bodies can be severe enough to cause serious injury or death. This is referred to as the second crash, the point after the vehicle crash where occupants collide with the car's interior. Stop the program and complete activity number 1. When finished, continue watching the program.
In order to reduce injuries in this second crash, safety systems are designed to allow the occupants to ride down the crash. This means to stop more gradually over a greater distance so that the deceleration of the occupants can be as slow as possible.
Each year, auto manufacturers crash test hundreds of vehicles from every angle to measure the results of various impacts. Often included in these tests are anthropomorphic test dummies that are designed to measure, as closely as possible, how the human body would respond in an actual crash. The dummies are equipped with sensors that detect crash forces in the legs, head, chest, and other locations. This information gives engineers and medical personnel valuable information on how crashes affect the human anatomy.
In low-speed accidents, the car's bumpers take the brunt of the impact. Let's take a look at their design to see just how the bumpers cushion the impact.
The bumper assemblies of modern vehicles are designed to absorb the energy in a low-speed impact. This is done by constructing the bumper assemblies out of an energy-absorbing foam that is stiff but will deform upon impact. Other vehicles have used energy-absorbing hydraulic cylinders similar to shock absorbers, mounted between the vehicle chassis and the bumper. In a low-speed crash, the bumpers of a vehicle are designed to absorb a great deal of the impact and reduce damage to the vehicle. In tests, passenger vehicles are subjected to 1.5 mile per hour and 2.5 mile per hour impacts from a pendulum-like device whose weight is equal to the weight of the vehicle, followed by 2.5 mile per hour forward and rearward fixed barrier impacts. After the impacts, there should be no defects in major systems, such as the lighting system and reflectors. The hood, trunk, and doors must operate normally. There should be no fuel, exhaust, or cooling system damage. The engine and transmission should operate normally, and all other systems, such as braking, suspension, and steering, should be undamaged as well. If the energy-absorbing material is compressed, it must return to its original contour within 30 minutes after the impact.
Let's now look at the two major design features a safe vehicle must have.
First, the structure of the passenger compartment must be strong enough to resist crash forces and help provide what engineers call survival space. This forms a steel cocoon designed to minimize the effects of the crash from intruding directly into the passenger compartment. Second, the passenger compartment is surrounded with material that deforms to help soften the impact. Not padding like we found in the catcher's mitt, but steel, the car's body structures. The more these structures crush, the more crash energy they absorb. These crushable structures are designed in actual crash tests and on computers in order to predict how crash forces affect a vehicle. In a crash, deceleration forces start immediately, but vary as the crash progresses, so that the deceleration of the passenger compartment is at a constant rate, minimizing the force experienced by the passengers. If the front structure is too stiff, it stops the passenger compartment faster in a frontal collision, putting greater deceleration forces on the passengers. Older vehicles that were not designed to crush the way today's vehicles are very often appeared undamaged in an accident, but their occupants were often severely injured within the unyielding structure.
If the structure is too soft, it will not absorb all the crash energy as it crushes. At the end of its crush, the passenger compartment and passengers will be forced to absorb the remaining energy.
In absorbing the crash forces of an accident, vehicles may be severely damaged. Often, the forces of impact travel through the body panels and up the body pillars, buckling the roof and other panels. This is intentional and allows the deceleration forces to be spread out on the outside of the vehicle, while protecting those inside the passenger compartment. Also, in an accident, any rotating or pitching motions of the car must be minimized so that the passengers decelerate in a direction that takes advantage of the vehicle's occupant restraint systems. This motion control is achieved by making the crush progressive. This means that the structure is softer at the outer ends, enough to ensure that the crush starts at the point of impact, then progresses toward the passenger compartment, which is stiffer and more crush resistant. Stop the program and complete activity number 2. When finished, continue watching the program.
As the driver moves forward during the crash, however, the steering wheel and column represent a potential hazard. Let's look more closely at these components.
Because the steering wheel and column are a major source of injury to the driver, in a frontal crash, the steering column is designed to be energy-absorbing and non-intrusive. Energy-absorbing columns have to serve 2 functions. First, they must stop the steering wheel and column from being pushed toward the driver as the front of the car crushes. Also, the energy-absorbing column must provide the driver with an impact force that is tolerable when he or she strikes the steering wheel. At the point of impact, the column should maintain the load on the driver's chest to a survivable level, and then deform under that load to protect the driver. Also, the system must be designed so that under crash conditions, the wheel stays in such a position so that it will strike the driver's chest and not move upward into the face area or downward into the abdomen. To achieve this, the steering shaft is generally made of 2 tubes, one placed inside the other. Plastic is injected between the 2 sections to lock them together. Upon severe impact to the steering wheel, the plastic shears and the 2 sections telescope inward, thereby absorbing the impact. Similar telescoping characteristics are built into other components in the steering column. Regulations mandate that in a 30-mile-per-hour frontal impact into a fixed barrier, which is equivalent to a 60-mile-per-hour impact into a parked car, the upper end of the steering column and shaft of a passenger car must not be pushed rearward more than 5 inches. There are also regulations placed on the steering wheel with regard to the amount of energy it must absorb. The steering wheel and attachments, such as the horn button, must also be constructed so that they will not snag clothing or jewelry.
A vehicle must also undergo other rigorous testing before it can be sold to the public. For example, to minimize potential fire hazards during and immediately following a crash, regulations state that a vehicle with the fuel system filled 90 to 95% of usable capacity must not lose more than 1 ounce of fuel during the impact, or a total of 5 ounces of fuel during the first 5 minutes after the impact. This specification holds for a 30-mile-per-hour frontal impact into a fixed barrier, as well as in rear collisions where a stationary test vehicle is hit from the rear with a moving barrier. Vehicles are also tested for fuel leakage during a 20-mile-per-hour side impact, where the same leakage standards apply. Following either a front, rear, or side barrier test, the crash test vehicle is rotated through 270 degrees to simulate a rollover crash. The vehicle is held at 90, 180, and 270 degrees for 5 minutes to measure fuel leakage. Again, no more than 5 ounces of fuel can leak during each 5-minute period. To further protect the occupants in rollover accidents, passenger car roofs are tested for crush resistance. A rigid, unyielding block with its lower surface formed as a flat rectangle, 30 inches by 72 inches, is applied to either side of the forward edge of the roof. When a force, the lesser of 1.5 times the vehicle's weight, or 5,000 pounds, is applied, the roof must not move inward more than 5 inches. Another crush resistance test is the dynamic rollover test. Here, crash test dummies are placed in the test vehicle, and the vehicle is placed sideways on a wheeled platform at an angle of 23 degrees. The platform is taken to a speed of 30 miles per hour and suddenly stopped, which flips the vehicle over. After this test, data collected from the dummy sensors is examined to determine how the rollover would have affected human occupants.
While a vehicle may crush to absorb frontal or rear impacts, occupant protection in side impacts requires a different approach.
Since there is very little crush space between the outside of the door and the occupants of the vehicle, the doors and related hardware must be as strong as possible to prevent the crash from intruding into the passenger compartment. This is achieved by reinforcing the doors with a high-strength steel barrier that spans the width of the door. In combination with anti-burst hinge and latch systems, this reinforcement spreads the force created during a side impact over a greater area and into the door pillars themselves. To test the effects of a side impact, the vehicle is hit on the side with a moving deformable barrier traveling at 33.5 miles per hour. Again, the data collected from the dummy's sensors is examined to determine how the side impact would have affected human occupants. In the event of a frontal, rear, side, or rollover crash, the doors must remain closed so that the occupants are not thrown from the vehicle.
To further reduce the possibility of pelvic injury, armrests and door panels must meet certain criteria as well. Specifically, they must be made of energy-absorbing material that can deflect or collapse inward at least 2 inches before contacting a rigid surface, such as the metal door panel.
Stop the program and complete activity number 3. When finished, continue watching the program.
In other areas, the interior of the vehicle is also designed to be as soft as possible to minimize impact injuries within the vehicle.
Older vehicles frequently used hard metal knobs and levers that stuck out from the dashboard. These unyielding surfaces often caused severe injuries in a vehicle crash. On today's vehicles, portions of the instrument panel and the seat back head area are padded. Head restraints must be provided for both front seat positions as well. The head restraint is designed to limit head and neck injuries in rear-end collisions. In this type of collision, the vehicle is suddenly pushed forward and the occupant is pressed against the seat back. However, tremendous forces are placed on the neck and spine as they are snapped rearward during the impact. For testing purposes, a 6.5-inch diameter head form located 2.5 inches below the top of a fully extended head restraint is used to apply a load of 200 pounds to the seat back. To simulate the rearward movement and compression of the backrest during a rear-end collision, a pressure of 275 foot-pounds is applied to the seat back to determine where the occupant's torso will be in a rear-end collision. During the test, the head form must not be displaced rearward more than 4 inches relative to the torso line of the compressed seat back.
For restraints and other safety systems to operate properly, the vehicle's occupants should remain relatively stationary during an impact. Because of this, the seats and how they are anchored are quite important. Each seat, except side-facing jump seats, must withstand a load 20 times the weight of the seat assembly applied forward and rearward to the seat. The upper cross member of the seat back at each seating position must withstand 275 foot-pounds of torque applied in a rearward longitudinal direction for forward-facing seats and in a forward longitudinal direction for rearward-facing seats.
To reduce injuries from hitting the windshield, a laminate known as high-penetration resistant glass is used. Here, interior and exterior surfaces of glass are held together by layers of plastic.
When the high-penetration resistant windshield is broken, the layers of glass are held together by the layer of plastic between them.
Different types of glass are used in the side and rear windows. This glass is called tempered glass. It is made harder and stronger by chemically or thermally treating the glass when it is manufactured. Tempered glass has a far superior strength-to-weight ratio than conventional glass. When broken, tempered glass breaks into relatively small bits instead of the large, more jagged shards of conventional glass. Regulations state that when broken, the individual pieces should not weigh more than 0.15 ounce. Tempered glass is more flexible and more resistant to impact from hail and door slamming than conventional glass, and is therefore used in side and rear window applications. Other systems are also designed with safety in mind. For example, vehicles with electric fuel pumps often have an inertia switch designed to open the circuit in the event of a vehicle crash. The pump itself often contains a check valve that stops the flow of fuel in the event of a rollover. Other vehicles equipped with electric pumps are high side or positively operated electrically. This design ensures that an electrical short to ground in the event of an accident will stop power flow to the pump. Stop the program and complete activity number 4. When finished, continue watching the program. Now let's review the key elements in this program.
1. Passive safety systems are designed to protect vehicle occupants during a crash.
2. During a crash, a vehicle's body panels are designed to crumple and absorb the kinetic energy stored in the vehicle.
3. Because the steering wheel and column are a major source of injury to the driver, the steering column is designed to be energy absorbing.